Today we're going to learn about crystal structure of solids and also one other section. Forces that hold solids together and what causes different melting points in solids. But we'll start with crystal structure. So here I've got three different possible crystal lattice structures. The first is a simple cubic crystal, right there. This is a body-centered crystal, where in the very center there is either an atom or an ion or a molecule, and then on the outside of the cube there's also an atom, ion, or molecule. There's also something called a face-centered, where on each face of the cube there is an atom, ion, or molecule, in addition to each of the corners of the cube. You don't need to memorize the names of these, just to give you an idea of when you have a crystal structure, the molecules, ions, or atoms are all very ordered. So these are the one cube where the cube wouldn't be next to another, next to another, next to another, and form a great big crystal structure that can be made of this type of cubic, or this cubic, or this cubic. You'll see some pictures of these a little bit later. All right, bonding in solids. We're going to classify solids as four types: molecular, metallic, ionic, and covalent. These covalent ones, you might think that they're molecular because they're made only of nonmetals, but they're called macromolecules as well. We call them covalent network solids. And here's some information about each of these. So this is going to be a chart summarizing what type of solid we have, some examples, whether the melting temperatures would be high or low, and what forces are holding the particles next to each other in their crystal structure form. These gray lines here, black lines, those would be considered the forces holding the different particles. The red dots are the particles, and the lines along here would be the forces holding particles together. In a network covalent solid, those forces are actually covalent bonds, which is why it's called a covalent solid. All right, so first, molecular. We've actually discussed molecular in section 12.2. Molecular solids have three types of forces: dispersion, dipole-dipole, and hydrogen bonding. We've already discussed that dispersion is the weakest. Next strongest is dipole, next strongest is hydrogen bonding. Now, while hydrogen bonding is stronger than these other two forces, it's actually one of the weakest of all of the types of forces that bind solids, the particles in solids, together. You'll see that in a moment. Okay, metallic solids, chromium, silver, any metal would be a metallic solid. Metallic solids typically have very high melting points, and we wouldn't compare two metals with one another. They're held together through metallic bonding, and again, you'll see a model of that a little bit later. Ionic crystals, those would be made up of nonmetals and metals, because ionic compounds have metals and nonmetals in them. Here's a few examples. Ionic crystal solids have high melting points. The forces holding them together are the ionic bonds, or we could also think of it as the lattice energy. So the bigger the lattice energy, the stronger the ionic bond. And lattice energy we learned a bit earlier. The positive ion charge times the negative ion charge over the radius, the distance between the two nuclei. So the higher the charge magnitude, the higher the melting point. The smaller the ion, which means smaller r, makes also a higher melting point. All right, last of the solids. Notice we're going from low melting point to high melting point. However, between metallic and ionic, we don't compare these two. They're both just high. There's no way to know for sure which one would be higher than the other, and we won't compare between metallic and ionic. Okay, network covalent solids. Examples would be carbon and glass. Those are the only two that you are responsible for knowing. These have the highest melting points of all solids. That's because you have to actually break covalent bonds. So in our lattice structure, if we have a molecule, let's say these red dots were all molecules, the things holding those molecules in place would just be our intermolecular forces. The intermolecular forces: dispersion, dipole-dipole, hydrogen bonding. But if one of these was a network covalent solid, suppose we had a network covalent solid right there, that would mean that each of these red balls was an atom, and each atom would be bonded to another atom in the structure. In order to melt, you'd have to break all of these covalent bonds. Covalent bonds are much, much stronger than just intermolecular forces, these right here. So you need a lot of energy to break apart the covalent bonds and melt the network covalent solid. So these have the highest melting points of all solids. There's a little note down here. Some things that students forget. So this is a very important little note here. Molecules have the weakest forces. In the last section from the last lecture, we learned that hydrogen bonding is the strongest of the intermolecular forces, but those are still weaker than metallic bonding, ionic bonding, or covalent bonding. Okay, so molecules have the lowest melting points of all solids. The weaker the force, the lower the melting and boiling point. Okay, so just reminding you again, what's weakest, what's strongest? And then you won't ever be asked to compare the strengths of forces between ionic and metallic substances. All right, so now we're going to look at some models of each of these. First, we're going to look at molecular solids. So at the lattice point of each cube, each point in the cube, we would have a whole molecule. So here's a molecule, here's a molecule, here's a molecule, here's a molecule. And the molecules are held together by intermolecular forces. That could be London dispersion, van der Waals, dipole-dipole forces if you have polar molecules, or hydrogen bonding if you have molecules capable of hydrogen bonding. The little green dots here, those dashes, they're not dots, they're dashes. The little green dashes here are showing you the intermolecular forces keeping this molecule and this molecule in place. So everywhere where you see these green dashes, they look green to me anyway, that would be representing your intermolecular forces. Here's another example of a solid and its crystal lattice structure. This is iodine. So each corner of the crystal lattice, wherever you see a molecule, it's an iodine molecule. The molecules are not bonded to other iodine molecules, but they are held together by intermolecular forces. In this case, iodine is nonpolar, so what's the only force holding these in place? London dispersion. Okay, let's move on to our metals. Oh, we've got our little sea of electrons right over here. I like how these things move. Okay, so metallic solids. In a metallic solid, you'd have your atom at each crystal lattice corner, or in the center or on the face of the cubic body. And those atoms are actually positive ions. They would be considered cations in a sea of electrons because the valence electrons, those valence electrons for any particular metal, they are free to roam around throughout the whole metal structure. Now these look like they're kind of stuck in place, but they're not. They could actually roam anywhere in this structure. And this is why metals can conduct electricity, because you have these electrons that are free floating. The cations themselves are stuck in place. They cannot move. Notice the yellow cations here. They have a little plus charge. Those are the core of your metal atoms. And then the valence electrons, that's what can move. So those negative charged electrons can conduct electricity throughout the whole metal. Okay, moving on. Ionic solids. Nothing's moving. You're stuck in place. So can ionic solids conduct electricity? No, they cannot, because nothing's moving. Do you see anything moving here? I don't. But what we have is, again, our lattice structure, and we have, this would be your anion and a cation. Cations are always smaller because they've lost electrons. Anions are bigger. So you have your cations and anions neatly organized into a crystal lattice structure, and we have to break those ionic bonds in order to melt. Last, our network covalent solids. Here's our model of diamond, pure carbon. Notice the black balls, those are all carbon atoms. And notice the carbon atoms are all bonded to another atom somewhere in this structure. In order to melt this, I've got to break Do you hear me breaking the bonds? You can't actually see it happening because it doesn't work that way. But in order to melt this, every single one of these covalent bonds needs to break. That's a huge amount of energy, so you need a really high temperature. On the right, we have a model of silicon dioxide, which is a network of silicon and oxygen. And again, in order to melt this whole structure, we've got to break every single covalent bond in here, lots and lots of energy. So now we're going to do some actual problems figuring out the types of molecular solids that two substances are, and also which of two substances would have stronger forces. So we're going to have problems where we have two examples. So we're going to compare hydrogen gas versus sodium. We're going to find the forces holding each substance together in the solid phase. And then we're going to determine which of these two has stronger forces and thus a higher melting and boiling point. So in order to do these problems, first you want to find out if the substance is molecular, ionic, metallic, or a network covalent solid. And then we go through the chart on the previous page. Let's move this up a little bit. We go through this chart to see which substance has the strongest forces. So let's go back. Here we go. So we look at hydrogen, and we know that hydrogen is made of only nonmetals. So this would be a molecule. It's not a network covalent solid. And there's only one bond. We know this is nonpolar because it's H bonded to H. So we know that hydrogen is a nonpolar molecule and has only dispersion forces. Sodium, if you look on the periodic table, sodium is a metal. So let's look over here. Why does it keep going back? Okay. So dispersion, it's the lowest melting temp of all the different crystalline solids. So the hydrogen would have the lowest melting temp. And sodium is held together, it's a metallic crystal, would form a metallic crystal. And those are held together by metallic bonding. And sodium would have a higher melting temp. Oop. And here you go. There's the whole explanation of what I just said. Okay, next problem. Okay, so the next problem we're going to look at sodium chloride versus sodium oxide. First, we're told we have to find out if the things are molecular, ionic, metallic, or a network covalent solid. Sodium chloride, metal, nonmetal, therefore this is ionic. Sodium oxide, metal, nonmetal, ionic. I've got two ionic compounds. When I have two ionic compounds, let's go look at the chart and see what we need to do. Ionic compounds. If we want to compare two ionic compounds, a way to compare if possible, so we're going to look in this column. How do we compare them? Recall, lattice energy is Q plus times Q minus over R. It's the charge magnitude over the radius. So first we'll check the charge magnitude. Let's go back over. So Na, you look up Na, it's in the +1 column. Well, Na is the same in each of these, so we ignore the Nas. But the chloride, -1 charge, oxygen -2 charge. So who has the bigger charge magnitude? This one. We've got a +1 and a -2. So +1 times -2 is -2. +1 times -1 is only -1. This has a bigger charge magnitude, and therefore a higher melting point. And there you go. There's the summary of it all. You can write it down in your own words or whatever makes sense to you. Now if you want to pause, you can pause this, and then you're going to see the answer in a moment. I'll talk you through it. We need a little bit of space here though. Okay, NH3, N is a nonmetal, H is a nonmetal. Therefore this thing is a molecular crystal. When we have molecular crystals, if we have more than 2 atoms, we need to actually draw Lewis structures. So you need the Lewis structure for N. When you do the Lewis structure and you get the geometry, you find that this is trigonal pyramidal. And then we have to put on our bond dipoles, N is more electronegative than H, so we're going to put on our bond dipoles, pointing to the N, because N is more electronegative than the H. Now we're going to add up our bond dipoles. I'm going to start number 1, number 2, number 3. Start on the left and just add them. Same direction, same size. Doop. That does not equal 0, therefore this is polar. Okay, so you should notice something else. I've got H bonded to N. If H is bonded to N, I also have hydrogen bonding. So NH3 has London dispersion, dipole-dipole, and hydrogen bonding intermolecular forces. Carbon, ooh, that's a special one. You have to always be aware of carbon. It's our network covalent solid. C, pure carbon. Any form of pure carbon, whether it's diamond or graphite or coal, very high melting point. In fact, coal is going to actually combust before you can melt it. And it has the highest, remember that column is our melting temperature. So carbon has the highest melting temperature of all of the crystalline solids. And the forces holding that whole big network covalent solid together is covalent bonds. We've got to break all the covalent bonds in order to melt pure carbon. So carbon has the higher melting point. There you go. There's your full and complete answer. You can pause and write that down, or you might have already written it down. And last one, oops, okay. Go ahead and pause it if you want to do these on your own. You should notice they're both molecules, so we're going to have to do Lewis structures. I'm going to show you how to do that right now. SO3 looks like this. Oh, I've switched the colors. It's trigonal planar. And we're going to point to the O's because O's are more electronegative than S. And now we need to add our bond dipoles. So there's the up one. That's number 1. I'm going to add 1, then 2, then 3. So the second one goes down into the right, and the third one goes down into the left. And I pretty much started and ended at the same place. That equals 0. Therefore, this is nonpolar. SO3, sulfur trioxide, is nonpolar. So sulfur trioxide has only London dispersion forces. Only London dispersion forces. Cl2, 2 nonmetals bonded together. The bond cannot be polar because it's a Cl bonded to a Cl. Therefore, Cl2 is nonpolar also. And when you have 2 things that are nonpolar, let's see, what do we have to check? Let's look in our handy-dandy chart. Melting temps and way to compare if possible. Let's see. So we know that these have very low melting temps. If you're comparing 2 nonpolar molecules, the one with more total electrons has stronger dispersion forces and a higher melting point. Okay, let's check it out. Oops. So if we add up all the electrons on the S and all the electrons on the Cl2, we find out, not the S, the SO3. SO3 has 40 total electrons. Cl2 has 34 total electrons. And so who has stronger forces? Sulfur trioxide has more electrons, so it's more easily polarized and has stronger dispersion forces, and therefore a higher melting temperature. Okay, another little quick aside here on solubility. So we sometimes will talk about, this is not about crystalline solids at this point. This is a total side note, but it's something you must know. This is talking about liquids dissolving in liquids. Like dissolves like. Polar molecules dissolve in polar molecules. Nonpolar molecules dissolve in nonpolar molecules. So if you have a polar molecule and a nonpolar molecule, they will not dissolve in each other, and they are said to be immiscible. They are immiscible. Okay, that's it.